Hello and welcome back to Calculus 2. We are going into chapter 11 tonight, and we are going to also take a look a little bit at the exam review, just the list at the end of the class. And then the next week we will take care of the rest of the stuff as much as possible. Before I start this, I'm just going to point out that I placed the course survey thing we talked about last time. It's available with the rest of your homework in my MATLAB. So please go there and take that, start working on it. It's due the day of the final, but it's also, I think, 40, 50 problems, whatever it is. It covers all of the chapters. It's a course survey, so everything from 6.2 all the way through chapter 12. Keep working on it as much as you can, as soon as possible, so you don't have to. So there is no project this semester. This will be replacing the labs and so on. I will post in the announcements exactly how the new grade calculation works and so on, so you can make your decisions. Just give me a little bit more time. I'm drowning in all the stuff that I have to do. So let's talk about power series. So far we dealt with the creatures like sequence, and that was AN, which had members A0, A1, A2, A3, That was just the ordered list of numbers. Then we dealt with a series, which was the sum of the sequence, and we particularly dealt with the ones that are infinite series, and that was A0 plus A1 plus A2 plus A3 plus ... going forever. The goal for today and for chapter 11 is to learn one of the most powerful creatures in mathematics called the power series, and this thing will be used in many of your courses later on, especially when you transfer. Many of the calculations depend on ability to deal with power series because they do one very nice thing for us. So the goal today is to learn about power series, which would look like this. We can give it a name, but then we don't have to. Let's just leave it like that and say it is the series that goes from, I don't know, can go 0 to infinity of Cn x to the n. Now, if I write out the terms for this thing, you should immediately recognize it as something that you already know. So if I go and write the terms, the first term is a zero term, so that's a C0, and then x to the 0, that's 1, plus C1x plus C2x squared plus C3x cubed plus ... Cn x to the n plus ... going forever. I hope that this part here you would recognize from your pre-calculus course as a definition for what? I know there is a delay and, to answer the question. The thing that you see boxed in before that plus ... is a definition for polynomial. So you have your constant polynomial, you have your linear polynomial y equal mx plus b, you have your quadratic polynomial x squared, right, ax squared plus bx plus c, your cubic polynomial. So all of the polynomial powers that you learned ever, they're all here in this thing. It's ordered through n. All of the powers are there, right? 0, 1, 2, 3, 4, all the way, going to infinity. See, this is kind of infinite polynomial, and that's a, different creature than what you're used to, because now we don't have the highest leading term and all of that. It just keeps going and going and going. And this is really, really important in mathematics, and you will see that many courses will use this, because essentially what this thing does for us, it turns functions into polynomials. And you need to immediately understand and appreciate how insanely important that is. You have a function that you cannot integrate. It's way too annoying. Whatever reasons you have, turn it into a polynomial and make a joke out of it, right? So there are some restrictions and a lot of things you have to be very careful about. But the essence of this is, right, and that's for 11.4, to take a function and write it and rewrite that function into a close enough polynomial. And when you have it as a close enough polynomial, integrating or differentiating or doing whatever with it is a joke, other than finding roots, obviously. But figuring out anything else is a joke. And that's why these power series are so damn important and so powerful and needed and necessary, right? So all of that. So the actual definition for power series, so I'm going is the one in red. Now that one is centered at 0. We'll see what that means, but for now we need to say that this one is centered at 0. Now the general case is where it's centered at some value a. We'll understand what that means when we start dealing with this in more detail. So we'll have to actually improve on this and write it as x minus a to the n, which when we expand, we'll just get this x minus a everywhere. So this is centered at x equals a. So at some value a. And that's the one that takes care of everything for us. We'll deal with that when we get there. Now, before we go and do the details of this, we want to first recall something that you should know and remember from your Calculus 1 class, which was called linear approximation. As what this thing is going to do is going to approximate our functions to the best of its abilities, and we'll see that those approximations are insanely good. So what you learned in Calc 1, and I spelled it with K's because I'm a boss. You learned linear approximation, where you learned that the linear approximation L was f of a plus f prime at a times x minus a. Well, wait, when I plug in a number in f, I get a number. When I plug in a number into f prime, I get a number, and then I have x minus a. That's this much. I need you to see that that's it. It's a number plus a number times x minus a. So you have already learned in Calc 1, without knowing about it, you already learned the first two terms of the power series we are learning tonight. Your linear approximation are just the first two terms. Then you add the third one and the fourth one and the fifth one, and as high as you need to go for a precision that you need. So in Calc 1 you learned approximation, and then you use this one to figure out what is the square root of, I don't know, square root of 23, right? To the best of your abilities. Because you can calculate the square root of 23 using this. Square root of 23 has as a function f of x square root of x, and it has as this a 25 because that is the value that you can easily compute in this function. So your a is always the closest value that you would be able to compute without a calculator. Think of it that way. So later on when I say centered at a, it has to be centered, meaning it has to be close to what you actually want to compute. It has to be in that neighborhood, that area. We'll see, examples obviously for Calc 2 later on. This is still Calc 1. So now if I calculate my f prime of x, that's 1 over 2 root x. And now I can calculate L of x because we memorized the formula. That's f of a, which is square root of 25, plus the derivative of this times x minus 25. And when you simplify this, becomes 5 plus 1 over 10 x minus 25. And this is all Calc 1. So now, if I want to calculate square root of 23, that's approximately going to be L of 23. So instead of computing square root of 23, I'm computing this easy problem with 23. So I have 5 plus 23 minus 25 divided by 10. And that's 5 plus negative 2 over 10, which gives me 4.8 as a total. Now, if you go to your calculator and you punch in square root of 23, you will get, obviously, a lot of decimals on this one. So let's take a look. Square root of 23 gives me approximately, we have to have the squiggly equal because I'm going to round, 4.796. Well, that's pretty close to 4.8, if you ask me, right? So I have this calculation that we know from Calculus 1. The goal today is to make this even more precise by adding extra terms. Our what we call two-term approximation, because when you compare this infinite polynomial and this corresponds to only the first two terms. That's why I would say this is a two-term approximation. It only used two terms, and it got pretty damn close, right? I mean, if this 6 bumps that up, that would bump that up, and then that it's the same, right? If you round it that way. But see, this number worked out to be a round number from this calculation. We know that the square root of 23 is not exactly 4.8. I mean, go 4.8 squared, and you will see that you are not getting 25 or 23, right? But the thing is that if I put in another term, which we don't know yet what it is, so if I have this, and then I say plus f double prime, blah, 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 in that case, my result of 4.8 would be even better and closer to this. So we would get on a clean calculation over there, we would get 4.79 blah 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 something, right? So it will be way closer to what the calculator gives us than what we calculated with 2 terms. The more terms you have, the more calculations you do, but the better the precision of your answer, which is why you will be deciding, or you are told, how many terms you get to keep, how many terms you get to compute for every problem that you get to deal with. Now, power series, so back to power series. Power series are series which contain this x to the n business. Doesn't matter which one you write, right? The one that is centered at 0 when a is 0, or the one that is centered at a when a is something different than 0. They all have the same shape. There is this variable x raised to the n, or variable x minus a raised to the n. And that is defined and called power series. Now, power series will converge to a function, and we are now going to define what is called the Taylor series, and that's the reason why I always, when I teach calculus, with this book, I always combine sections 11 and 13 into a single section, because if you open the book and read the section, you will find the definition for Taylor series in section 11.1, and then section 11.3 is called Taylor series. Well, hold on. Why are you defining it in one and then, just 2 of these together? There is no reason to do something and then do it again. So, Taylor series. Taylor series is defined as the power series. We're going to use Pn of x for obvious reason, because we are going to get a polynomial, therefore p rather than f, right? P polynomial. And then we're going to define this. It's a power series, so it goes 0 to this. It's a Cn x minus a to the n. Now, what makes Taylor series a special power series is that we have a formula to calculate Cn's. Cn's are defined as the nth derivative of f computed at a divided by n factorial, for n starting at 0 and then 1, 2, 3, going on forever. This over here is your Taylor series. And we can convert functions into a polynomial using this. Let's go do the first example of compute power series for f of x equals e to the x. Now, this is the only case where power series is overkill, because e to the x is the only, constant as well, are the functions that it's easier than a polynomial for integration differentiation because it stays the same. But there are situations later on where you do have function composition with ease, what is an exponential function, and you try to integrate and it's a problem. So knowing this power series is actually very important and very beneficial. As I mentioned, if you are, if you have any dreams of becoming a real mechanical or electrical engineer or something like that, your 400 level courses and maybe even graduate if you go, they will be filled with these power series. I mean, differential equations is going to have it, right, in chapter 8, but I'm talking about partial differential equations. Like 90% of that course is power series. And that's a, standard course that most of you will have to take if you are in a STEM, right, when you transfer out. Learn this chapter very well. Let's go. What do I need? Well, clearly I need a whole bunch of derivatives, and luckily they're all the same. I did not specify that I want to center this at any value, which means center at 0. So when it's not specified, we center it at 0. And then it has a special name called Maclaurin series. Maclaurin series is Taylor series centered at 0. So if you're, say, centered at 1, centered at 5, you always call it Taylor series, and then centered at 0 is called Maclaurin series. It's the same thing, right? It's just special case of centering it at 0. So what do I have? I have a whole bunch of derivatives that I need, right? So my function f of x is e to the x, and then my first derivative is the same as the second derivative, is the same as the third derivative, it's the same as the fourth derivative. This is where notation switches to that parenthesis notation that we had before, and they're all e to the x. It's a boring function, right? So when I write out my power series, which is like the p of n of x is summation 0 to infinity of cn, in this case just x to the n, because I am not centering it at like 1 or 2 or something, is going to be c0 plus c1x plus c2x squared plus c3x to the 4th plus dot 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 plus cnx to the n plus dot dot dot. Now, each one of these c's has the formula to compute it. So c0 is the 0th derivative of the function computed at 0 divided by 0 factorial plus the first derivative of the function computed at 0 divided by 1 factorial plus the second derivative computed at 0 divided by 2 factorial. Why am I calculating f of 0 constantly? Well, because it's a, and we are centering at a. Since there is no mention of where this thing is centered, it's centered at 0. So no mention of center at blah blah means center it at 0, Maclaurin series, which means you will be plugging a 0 in each one of these derivatives. If I say center at 7, then a is equal to 7, and then each one of these numbers would be a 7 in these derivatives. So it's just, follow the formula, be careful. Oh my, I'm forgetting x to the 0, x to the 1, x squared, holy nightmare, plus f triple derivative there, computed at 0, divided by 3 factorial x cubed, plus the fourth derivative computed at 0 divided by 4 factorial, plus, and I'm just going to put 3 dots. I don't have to write this term in terms of these numbers because I can't compute it, so I'm just going to leave it. This over here tells me we're going to infinity, so I'm just going to leave it there because we do have infinity on top of our summation, right? So it has to go to infinity. Over here we just got to n equals 4, right? N equals 4 on the 5th term because the first term is 0, right? So 0 through 4 has 5 terms. You need to go to infinity because the power series is asking you to go to infinity. All right. 0, okay, so now I have to write some of these things because I'm not sure if you all know that, but zeroth derivative of the function is the function itself. So when I have the zeroth derivative of x, that's just actually f of x. And then f prime is the first derivative and so on. There are actually also half derivatives and quarter derivatives and all of that kind of stuff. Go look it up online. Math doesn't even scratch the surface with calculus, right? And also another thing to know is that 0 factorial is 1. That's also something that is defined. And that's something that you should know. All right, cool. So now if I want to compute all of that mess from up there, that means I need to compute e to the 0 divided by 1 times 1 plus e to the 0 divided by 1 times x plus e to the 0 divided by 2 times x squared plus e to the 0 divide... You know what? I'm going to leave the factorials in. Nah. We'll deal with it. Plus e to the 0 divided by 24 x to the 4 plus dot dot dot. When I solve all of this, each e to the 0, right, is equal to 1. That's also some, right, algebra stuff. So we have the first term is 1 divided by 1 times 1, that's just 1. Plus x squared over 2 plus x cubed over 6 plus x to the 4 over 24 plus dot dot dot, going on forever. What I just found out is that e to the x as a function can be written as this infinite polynomial. So if I want to compute certain things and I don't have a calculator, let's say you want to compute the value for e to the 0.3, right? We can use this to plug in 0.3 and get a pretty good answer just by, calculating these things with a stick and a sand, right? So we found this, and now we can write a nice compact formula. If you go back to this line here, but use factorials instead, we can combine this into summation 0 to infinity of x to the n divided by n factorial. You see that there is x to the 0, x to the 1, x to the 2, x to the 3, 4, 5, 6, 7. That's x to the n, right? Time e to the 0, that's just x to the n on top. And my denominators were 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial. That's n factorial. So we are able to rewrite the exponential function as this infinite polynomial. And now, if you want to compute stuff, now it has to be 0.3, 0.2, e to the negative 0.5, right? You want to be close to 0 because remember your a was 0. If you try to compute e to the 7.1 using this, it will be really wrong because 0 and 7 are really far apart. If you want to calculate e to 7.1 without a calculator, you have to come up with the formula centered at a equals 7, which means that this x on top will have x minus 7 in it. You have to be careful about those things. So it is not, it's not a free lunch that replaces everything you ever learned. This, you have to be careful, right? Use it responsibly. So if I want to compute this using 4 terms, well, that means 1, 2, 3, 4 terms. That's the 4 terms. You will literally replace x with 0.3 and do the calculations without a calculator. That's the reason why we are doing this, right? If we had the calculator handy, we just punch e to the 0.3, right? But you know which picture we're going to paint over here. It's the desert island and the batteries for the phone and the calculator ran out and the Wilson is gone. So now you have nothing to do. You want to build a shelter and e to the 0.3 popped up because you are an engineer, right? How do you compute this? Well, e to the 0.3 will be approximately equal to 1 plus 0.3 plus 0.3 squared over 2 plus 0.3 cubed over 6. That's the 4 terms. And now you compute these without a calculator, right? So 0.3 squared is 0.09 and 0.3 cubed is 0.0027, right? No, 0.27. Because you have 0.3, 0.3, 0.3. So that's 27, and you need 3 decimals. Good. All right. So now, plug these in and compute. So that's 1.3 plus 0.09 divided by 2 plus 0.027 divided by 6. A little bit of more calculations without a calculator. That's going to be 1.3 plus 0.045 plus, and now we have 27 divided by 6. So put 6 in front. 6 goes into this 4 times. That gives you 24. And then the leftover is a 3, put a 0, that's a 5 over there. So another 45, but that one is shifted 0.0045. That should be good. And now we just need to add these numbers. So as you can see, it's no calculator use, right? You just plow through this. 1.3495. Let's see. E raised to 0.3. Calculator. Computes e to 0.3 to be approximately 1.34985. Oh, come on, right? We are off on a 4th decimal. This is insanely good, right? Precise. Now, obviously, in the old days, this is what was used to right, this is what is used to calculate values because there were no calculators. Calculators are what, 50 years old at most, right? Prior to that, people walked around with a book with values, or when they needed something calculated, they computed it this way, right? Because you had to calculate everything by hand. Think about this, guys. Research to get to the moon in 60s, nuclear research done in 40s, no computers around, right? All of this was calculated by hand, right? No matter how complicated it was. And you need something correct to the 7th decimal, go ahead, use 6 terms, right? And go through calculations carefully and you will get it. So power series are very useful because they turn functions into polynomials. And then polynomials are easy to differentiate, integrate, they're easy to compute, right? You want to do everything with polynomials except looking for roots. They are a living nightmare to find zeros, right? But other than that, life is really nice and easy when you are dealing with polynomials. Let's convert another one. So compute power series for f of x equal, let's say, cosine x. I think the book did sine x, so you can go and read that one. I'm going to compute cosine x because I can. All right. So we know that for those coefficients, CNs, we are going to need derivatives. And let's compute, I don't know, first 6, 7, whatever terms, right? So we'll need quite a few derivatives here. And you will see why. Every other one is actually going to end up being 0 term. So, half of the terms that we compute, we're going to end up throwing away. So I can't do it like with the e to the x. I computed just 4 and it was good to go. Right over here, we have to compute like 6, 7, 8 terms because every other will be thrown away. So what do I have? I think Rory is trying to tell me that the stream is dying out. On my end, everything looks good, and I can hear my voice in the headphones from because I'm watching it myself on the other screen to make sure it's working. So I'm not sure if, hopefully it works. If it's not working, then just watch one of the old streams. They're all the same stuff, content. Anyway, so my function f of x is cosine x. My f prime of x is negative sine x. My f double prime of x is negative cosine x. My f triple prime of x is going to be sine x because the derivative of cosine is negative sine, and then they negative and negative cancel. Then the fourth derivative, now we're switching notation for derivatives from those tick marks, goes back to cosine x. The fifth derivative is negative sine x. The sixth derivative is negative cosine x. You see that it's just turning around. All right. We are, again, I did not say centered at some value. So, centered at a equals 0 again, right? So, I will remind you that your CNs are f, the derivative, computed at a, divided by n factorial. You see, every time when you run into sine of 0, that term is going to die because sine of 0 is 0. Every time you have a cosine of 0, that term is going to survive because you have cosine of 0 is 1. All right, let's plug all of this in. So what's my Pn of x for cosine? Well, the first term is just f of a. So that's, I can write it out. So f of 0 plus the f for n equals 1. That's the first derivative computed at 0 over 1 times x plus the second derivative computed at 0 divided by 2x squared, plus the third derivative computed at 0 divided by 3 factorial, which is 6, x cubed, plus, maybe I should put these factorials in, because life, then we'll compute. The fourth derivative notation switched at 0, 4 factorial, plus the fifth derivative of 0 divided by 5 factorial, plus, and I'm going to put 3 dots there, even though I have a sixth one, we can add it later. So this becomes cosine of 0 plus sine of 0 divided by 1 times x, plus negative cosine of 0 divided by 2x squared, plus negative sine of 0 divided by 6x cubed, plus positive cosine of 0 divided by 24x to the 4. Let's go more. Plus the fifth derivative, 1, 2, 3, 4. Fifth derivative is negative sine of 0 divided by 120 on the fifth derivative, that's x to the 5, plus negative cosine of 0 for the sixth derivative, 720 for the 6 factorial, x to the 6, plus dot 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 going forever. Now the fast way, the fast way of calculating these denominators here is just to multiply by the next number. This is your 1 factorial. For 2 factorial, you have the previous number times 2, then times 3, times 4, times 5. So as you can see, to get a 6, it's 2 times 3. To get 24, it's 6 times 4, because that's on the fourth one, and so on. So you just keep multiplying. So 24 times 5 is 120. 120 times 6 is 720. Then 720 times 7 for 4,000, right, and so on. So the goal over here is to now compute all of this. Now all of these terms with signs are gone. All of them. Because sine of 0 is 0, and that kills the whole term. So you are left with cosine of 0 is 1 minus x squared over 2 plus x to the 4 over 24 minus x to the 6 over 720 plus dot dot dot. And we just learned, right? We just learned that our derivative here, that our power series expansion for a cosine is this infinite polynomial here. And what we are going to do now is just write it as a formula, if you want, and then we can also write it in a compact form as well, right? So we can write that cosine of x is equal to 1 minus x squared over 2 plus x to the 4 over 24 minus x to the 6 over 720 plus dot dot dot. And you can use this to compute values of cosine close to 0. But you have to use radians. If you put cosine of 3 degrees and you put 3 into this thing, you will be really, really wrong. You have to be very, very careful. So, if you have 3 degrees, you have to convert 3 degrees into radians. That will be 0 point something small. Then you plug that 0 point whatever it is into each one of x's here, and you will compute cosine of 3 degrees closely. Otherwise, you are going to be really, really off. Now, I can condense this into a series notation. So this This makes an awesome tattoo, by the way. What do we have? We start with 0. We go to infinity, right? And what we see is we see alternation. We see -1 to the n, right? Because when n is 0, we have 1, which is positive. But then when n is 1, we have a negative term, right? And then n equals 2, but see, it has to be negative. Well, we'll fix that. Now, what else do we have? We have x to the all even numbers. The first one with the 0, right, kills that exponent, so it becomes x to the 0, which is 1, so that creates 1. Divided by all even factorials. The first one is 0. Well, 2 times 0 is 0. 0 factorial is 1. So everything works out to be 1 when n is equal to 0. All of them works out to be 1. So that's our first term. And then when I have n equals, for the next one, n equals to 1. What happens for n equals to 1? This becomes negative. Great, it is negative. This becomes x squared. Perfect. And this becomes 2 times 1, 2 factorial, which is 2. Excellent. It all worked out. Now, go n equals to 2. That better give us the next term. When n is equal to 2, I get this one -1 squared. That gives me positive. Perfect, it's positive. Then 2 times 2 is 4. Perfect. And then 2 times 2 is 4 factorial. 4 factorial is 24. So now we have the formula, the power series for cosine. And this formula here can be expanded to as many terms you want. If you want only 3 terms, well, that will end with x to the 4th, right? Because you have 0 term is the first, then n equals 1, n equals 2. That's 3 terms. If you need 7 terms for some bizarre reason, then you will go all the way from 0 to 6, right? And you will have 7 terms. 0 to 6 has 7 numbers. So you will have 7 terms. I have never seen anyone ever go to 7 terms. I have seen people go 3 or 4 terms, right? You might have a maniac who want to do 5 because, you know, I guess flexing. But, you know, 3 terms is 4 terms. That's plenty. You have seen the precision, right? You do 3, 4 terms, it's off on the 4th decimal. I mean, what do you need that precise, right? Your money is 2 decimals, and you know, the tolerances on cars, you know, when you build mechanical parts are, you know, tolerances are what? 10,000 at most, 1,000 usually. Not even pistons have that precision in making, and they are very sensitive on tolerances there, because those parts, those mechanical parts, are very tricky to make. So if pistons are not going to use that, I mean, unless you're working on quantum mechanics, there is no reason to go past 3 or 4 terms for any application ever for you guys, right? So keeping 3 terms, 4 terms is all we need. Now, what I'm saying is computing the function inside, computing the function in this power series rather than in function itself is good, but you have to see, you have to know how good your approximation is, how many terms you are using, and is it centered at the right value, and so on. So now we're going to take a look what's happening with the graph of original function and the graph of approximations. And I'm going to jump to the sign. So f of x is equal to sine x. And we are going to look at 0 to 2 pi interval. And I'm going to go with P0, which will be x, P1, x minus x cubed over 3 factorial, P2, x minus x cubed over 3 factorial plus x to the 5 over 5 factorial, and P3, which is 4 terms, x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial. You see, these are all finite polynomials. And I just want to see how well different approximations, right, Taylor series, when you chop it off, right? So for this first one, we threw all of this away, right? We throw that all in the garbage and we just keep the first term. Probably those of you paying attention in physics course, you probably heard your professor saying, sine x equals x for small angles. Hey! They're not crazy. They're not crazy. They're very practical, right? But there is that part of the sentence which they added for small angles. Small angles meaning close to 0. So it doesn't work if your angle is 90 degrees. It doesn't work if your angle is 48 degrees. It works only for small angles. And that actually is less than pi over 6. We'll see that now. So what I'm going to do is I'm going to jump into Desmos, which is already set. And I'm going to graph these 5 functions and see how well these P functions, the polynomial, right, Taylor functions, how well do they follow, how well do they bend around sine. So let's jump to Desmos, right, and start plotting these. Now I am interested only in this 0 to 2 pi. So I'm going to display 0 to 6, right? Because 0 to 6.28, 6.3 technically. So that's what I need. So my original function, right, that I need to graph is just sine x. And keep in mind that sine x, right, is our anchor function. And the P functions that I'm going to graph next, right, should be following this function here. So here is x, just x, right, and that's blue. Now, what we see is, first of make sure that you understand that your pi over 2, which corresponds to 90 degrees, is about 1.5, which is the peak for the sine. So when you are looking at that, then if 1.5, roughly 1.5, is your pi over 2, 90 degrees, then going down to half of that, around 0.75, is going to be your pi over 4. And you can see that the red line and the blue line agree roughly to maybe 0.5. So less than pi over 4. So that's what I said. If your angles are pi over 6 or less, right? Pi over 6 or less, then you can replace your sine x with just x, right? But then if the angle is a little bit more than pi over 6, leading towards pi over 4, let's say, then you toss in another term. And another term would be x minus, we have our x cubed, but that needs to be divided by 6. It creates this green line. Do you see that the green line follows the red line all the way past 1? They don't have exactly same values, but they have really good approximation for the y values from 0 to 1, let's say, right? So it's coming up on pi over 2. So these two terms are almost covering entire first quadrant of calculations. What are we going to do? Obviously, we are going to add another term, and that's our x to the 5. So I'm going to actually copy this because I'm lazy to type all of this mess. There we go. Copy, paste, and then plus x to the 5 divided by 120. That gives us this purple line. Do you see that the purple line is writing pretty much the same as as red line all the way up to 2? The more terms you add to your polynomial, the polynomial that you are getting is going to mimic and bend on the original function that it's derived from. So what I'm going to do is, right, I can add the 7th term now. Oh, kill me now, it's going to be 7 factorial. I could just type it in the 7 factorial. So copy this, and this one should cover all the way through pi. So Control V minus x to the 7th divided by 7 factorial. That gives me the black line, and you see that we almost reached pi calculation with 4 terms. Now, what I want you to understand that is we don't have to go this crazy because we have shifting. So we will shift the function and compute at the value we want. But I just want you to, quickly look at this first and say, wow, I can calculate from 0 to pi values for sine or cosine. I can calculate 0 to pi without shifting the function if I use 4 terms. Add in a 5th term, it will be precision past 3. So the more terms you have, the better approximation is. The Taylor series bends nicer and nicer and around the the original function f of x, and you will be able to use that to compute. Now, what if the sine, right? I wanted to compute the value. But the problem is centered at 2, let's say. If the problem is centered at 2, then every one of your x's, you're just going to say minus 2. And it will shift the graph, right, left or right, depending on minus 2 or plus 2 or whatever. It will shift the graph, and then you will be, you won't have to go as many terms, right? Again, when you see the red line, which is our original function, when you see the red line and any of the other lines, we have 4 other lines, the blue, purple, black, and green. When you see those 4 lines move away from the red line, we say they diverge from it. So the convergence of power series here, right, is on top of these. They converge to the function, but if you start chopping off terms, remember, the only way these are equal is when you have all infinity of polynomial terms in it. But that's not plausible for calculation. So you have to chop off the infinity of terms. So what do you keep? 2 terms, 3 terms, 4 terms? We already talked about it. The next term, the first term you throw away, is going to carry majority of error for the calculation. That piece of information is in 11.3, actually. So when I go from green to purple, right? From 2 terms to 3 terms, you see that the precision is better because the purple line rides the red line longer than the green line, right? Green line diverges from red sooner. That means that there is an error, right, that occurs, obviously, for your calculation. Now, most of that error that accumulates between the green and the purple, first of all, there is a green to red error, right? Green to red error. But then there is a green to purple. Also, green to purple has 1 term more, right? Most of the error that you get for these calculations is concentrated in the first term you throw away, which is why we say roughly, you calculate the order of the term you are throwing away, and that's the order of the error that you are making in calculation. So we can also make a prediction of how much error we are making with these approximations by throwing in terms, or throwing out terms, I should say. Back to our calculations here. So now, with this, armed with this knowledge, we can turn any function under the sun into this polynomial and keep whatever amount of terms you want to keep. Say you want, and those don't have to be just your basic functions, because remember, you can take derivative of anything, right? And because you can take derivative of anything, well, that means that you are able to find power series for anything. Now I'm just going to jump into the homework assignment and see if I can find a Taylor series centered at whatever. Here is a problem 21. It's a very cheap, easy problem. Says, find a Taylor polynomial for, they want a P3, so that's 4 terms, for function f of x equals x cubed, and they say centered at 1. Now, why would they want to center it at 1? Maybe you're supposed to calculate 1.27 cubed, right? So you're centering it at 1, so it's easier calculation. Anyway, P3. That means original term, function, and 3 derivatives. Your original function is always the first term, and then another 3 derivatives will give you P3 because it's a P0, P1, P2, P3, right? So I need 3 derivatives. Well, the first derivative is 3x squared. Second derivative is 6x. And the third derivative is 6. Now, we write our power series. It's going to be centered at 1. So we have to put x minus 1 every time. So I have my P3 will be C0 plus C1x minus 1 plus C2x minus 1 squared plus C3x minus 1 cubed. Now each one of these C's is using the derivative formula. C0 is just the original function. So I have P3 is equal to f of 1 plus f prime at 1 divided by 1, x minus 1, plus f double prime at 1 divided by 2, x minus 1 square, plus f triple prime of 1 divided by 3 factorial, that's 6, of x minus 1 cubed. So what is the P3 over here now? Well, this is going to be original function computed at 1. My original function is x cubed. So that's x cubed plus my derivative is 3x squared. So that's 3 times 1 squared times x minus 1. Plus my second derivative is 6x. That's 6 times 1 over 2 x minus 1 squared. Right? You just have to follow the formula. Right? It says calculate the second derivative at 1. Okay. Second derivative is 6x. And I'm supposed to compute that at 1. And finally, third derivative is just 6 divided by 6 times x minus 1 cubed. Deal with the mess. So that's going to be 1 plus 3 times x minus 1 plus 3 times x minus 1 squared plus 6 divided by 6 is 1, x minus 1 to the 3. That's your P3. You want to do more work? Foil all of this, right? You can. It will work out to be something. 1 plus 3x minus 3 plus, we gotta foil this and don't forget the middle term. So that's 3x squared. Middle term is minus 2, so minus 6x. And then plus 3. And now we expand this one. Coefficients are 1, 3, 3, 1. And then because a negative is positive, negative, positive, negative. Okay, so it becomes plus x cubed minus 3x squared plus 3x minus 1. If you don't know that, you can foil it on the side. I just know the formulas because I'm the boss. So I have one of these puppies. There we go. Now, where are my squares? They cancel. Right? So nothing for x squared because they canceled. I'm going to kill them off. Where are my single x's? There's this one. There's this one. There's this one. Oh, wait. They cancel as well. Oh, that's okay. We'll live. And finally, the constant. For the constant, I have plus 1 minus 1 and minus 3 and plus 3. We got x cubed. Now, those of you who understood the lecture, you could have just told me, oh, don't waste your time. You have to get the same x cubed. Because, come on, what are you doing? You are trying to approximate a polynomial with a polynomial? Really? Right? Of course you are going to get the same thing back. That's like going to buy $100. How would you buy $100? Well, you spend $100, right? Technically you swap the bills, but it's still $100. Taylor series are supposed to approximate non-polynomial functions by polynomials. Now, what they're going to return if you try approximating a polynomial, you're going to get the same thing. Just, right, this calculation shows that clearly, right? That if you try to come up with a polynomial expansion of a polynomial, you get the same polynomial back. That should be common sense. Maybe when you do more of these. So what is this good for? You got your trigs, you got your hyperbolics, you have your square roots, you have your logs, right? You have all of these other functions. And then in the next lecture, next class, we are going to learn one more piece of the puzzle. And that piece of the puzzle is that you can have function composition worked into this. You can have all of these kind of things that will set up the stage for calculus to kick in, so that you can integrate things that you couldn't integrate before. Now, a few more things that I mentioned that I didn't write down yet. The first thing is we're going to actually write the Maclaurin series, right? Because Maclaurin series is just a special name when you have your approximation at 0. I'm not going to go red for it. I'm just going to say Maclaurin series is Taylor series centered at a equals 0. So we do not get new calculations, we do not have new rules. It's just the name for pretty much every Taylor series we did today, because I centered the cosine at 0, e to the x I centered at 0, right? And the only one that was centered away from the 0 was this polynomial thing that worked out to be itself, right? So centering it at 0, we just have a special name for it. You are not going to be wrong if you call Maclaurin series Taylor series, because Maclaurin series is just a special case. Just like a square is a special case of a rectangle, right? It's a rectangle, all sides are the same. Circle, special case of ellipse, right? Radius is the same everywhere, where ellipse has two different, right, major and minor radius. So we are used to these special, right, names and special terms, but it's just still the same thing. Somewhere in the textbook, I still need to write the error down. Somewhere in the book, there it is, on page 740. Table of Taylor series. It is beneficial for you to memorize 4 of these, but you don't have to, right? It's beneficial for your later education. If you memorize 1 over 1 minus x, e to the x, sine x, and cosine x. If you memorize those, then you will see that it's very easy to remember 1 over 1 plus x, sine hyperbolic x, cosine hyperbolic x, because they will have minor changes. You know how cosine x had that negative 1 to the n in a power series? Cosine hyperbolic x is the same, we just take that term out, the negative 1 to the n. Take the alternation out, and that's your cosine hyperbolic. So same formula, just take away that one piece. It's very easy to remember those. So if you memorize these 4 here, then you can get another 3 for free, technically. And you will just know 7 at that point, which is cool. On the exam, you will be expected, which is exam 3 coming up next week, you will be expected to calculate from scratch. So I'm not going to ask you to memorize. I mean, plus you can just open the book and cheat, right? Because you're taking exam online rather than in the controlled environment. So, you should be learning this for your own benefit, so that once you run into differential equations, you're not asking ridiculous questions. You will just know what's going on. The last piece before we switch to the review is just to briefly talk about the error, right, term, which I mentioned. So one more time, our power series Pn is given as the series 0 to infinity Cn x minus a to the n. So over here there is infinitely many terms. Now, for calculation, we keep 2 or 3 or 4 terms, right? And we throw away the rest. So this introduces error. Because what have we done? We threw away terms, right? We threw away terms. And because we threw away terms, clearly that now those terms are not calculated in, and then there is error, right? So now, most of the error is concentrated in the first term you throw away. Most of the error is in the tablet is overheated, so it's gonna start doing weird things. First term we throw out. So if you are calculating P3, which is C0 plus C1 x minus a plus C2 x minus a squared plus C3 x minus a cubed, the error is approximated by C4 x minus a to the 4, right? Now we do have a nice formula where we say we call the remainder A as remainder R. Actually, capital R. And just a formula, so remainder Rn of x is your f of n plus 1 computed at some value c of n plus 1 factorial. You see, that's just a next derivative, next factorial, computed at x minus a for the next power. So if you are computing P3, then all of these are 3 plus 1, 4, right? Now, this c is in between your values x and a, or they can be a, c, x, right? Depending on what the problem is. It is okay for purposes of obviously all the calculation, it is okay to use a, right? So I could have written the formula just for the mathematical rigor. I have to put c, but when you are calculating, you can use a. And you can approximate error, right? So if they say, how many terms do I need to get the precision of, 6 decimal places? Just pick a random term and compute and see how many decimals you have in your answer, right? If you start with a 6th decimal and then other decimals, well, you just hit the money right there, right? If you didn't get the same, you just go 1 term less, 1 term more, right? And figure it out. Generally, as I said, all the calculations are 3 or 4 terms at most. That's technically what this is. The next lecture is a combination of 11.2 and 11.4. I teach this every time the same. I always combine 1 and 3, and I always combine 2 and 4. This is not a special case. If you go back in my YouTube channel for years, as far as the edition of the book is, you will find that all of my Calc 2 lectures are always 11.1 and 3 combined and 11.2 and 4 combined, because they are the same, 11.2 preps you for 11.4, and 11.1 and 11.3 are the same lesson anyway. So even the title is the same content. I will be back in less than 5 minutes with a review for exam 3, which is scheduled. I have to look at my cheat sheet. Exam 3, chapters 10 and 11, scheduled Friday to Sunday, 5/8 through 5/10. Announcement obviously will be posted very soon, but that's, it's the next. So exam is like 10 days from now. And as soon as your exam ends, your final exam will start. So I think exam 3 closes at noon, and final starts at noon the same day. And then you have another 3 days for the final, right? You have the 10th, 11th, and 12th. The final will close at midnight. So let's go do the list. On the Monday, we are going to cover Tuesday class, we are going to cover 11.2 and 11.4. That ends the chapter. And then Thursday, we'll do chapter 12 and the review. Then you have your exam. And then the next week, we can have more review and so on. So that's what we have. Right. I'll be back in 2 minutes.